Our project was sponsored by Collins Aerospace, a Fortune 50 company with a large manufacturing facility located in Windsor Locks, Connecticut. Their current HVAC system was installed in the 1950s, and intermittent upgrades to the surrounding campus have created demands that the original design cannot efficiently handle. The project goal was to physically map the chilled water piping system and analyze where inefficiencies can be optimized. Chilled water is generated, distributed, and consumed by heat exchangers that control workspace temperature. To model the network, theoretical performance of each heat exchanger was analyzed using heat transfer rate and heat exchanger efficiency. Assumptions like negligible heat loss when transporting chilled water and constant volume regardless of pressure or temperature are supported using MATLAB graphs with governing equations.
Hello, my name is Eugene, and I will be presenting the pipe flow model and simulations that we have run. All the models being shown represent the cogen and fuel cell module loops and not the entire system as a whole, and this is solely based off the limitations that we were faced with during this project. So the color gradients that you're seeing represent the pressure and how it changes throughout the system. The red representing the higher pressure, and the green representing the lower pressure, and the yellow is the medium in between them. So we actually discovered that these two flow loops work fairly efficiently, and since they're relatively close together in space, there's not a lot of room for them to lose pressure drastically. So in order to get a better idea of how the system would operate as a whole and not just these two flow loops, we actually introduced artificial inefficiencies in the form of fixed DP devices. And as you can see, there is a color difference between the last model and this one because of it. So we actually implemented a change by adding a booster pump to the fuel cell module loop, and this was because we found that the most hydraulically remote process load was located in this loop, which meant that the initial pump was discharging a minimum pressure in order to satisfy this load. So this meant that the cogen loop was actually being overpumped too. We actually discovered that the cogen loop only required around 25 psig, while the fuel cell module loop required 30. So because of this, we added the booster pump to the fuel cell module loop, since we already knew that the cogen loop was already being overpumped too. And because of this addition, we were able to set the initial pump to operate at a lower discharge pressure, because the booster pump would supplement the initial pressure coming into it to satisfy the fuel cell module loop. And we ultimately discovered that having this arrangement compared to the original arrangement that's currently being used actually reduces the total energy consumption.
Hello everyone, my name is Kyle Laxton and I'm a UConn senior chemical engineering student, and today I will be providing a quick breakdown of how our group used MATLAB in order to determine the most optimal operating parameters for the chilled water system at Collins. Because of the sheer size of the system, there are many inefficiencies to account for, and therefore I'll be breaking down the system into two parts. Now, to optimize the usage of air handlers, each individual air handler has its own specifications that will be thrown into this very long MATLAB code to eventually return the most optimal pressure we need to satisfy the heat load demand of each air handler. The three plots on the screen demonstrates different air handlers, and the red lines represent their respective pressures to meet that heat load demand. This MATLAB code also solves for many different parameters and can also be used to find the range of pressures needed to meet the heat load demands throughout the entire year. Now, to optimize the chillers, we will take advantage of the efficiency curves of each of the 5 chillers at Collins. By using energy consumption data from 2019 as shown on the screen, we can determine the average heat loads of different seasons. By taking the average heat loads and arranging these percent loads of chillers as a nonlinear constraint problem, we can actually use MATLAB to take the efficiency curves of each of the chillers and to determine the most optimal partial load of each chiller to meet the specified heat load demand. On the screen now is an example of what our chiller optimization code returns, and as you can see, it determines the most optimal operating conditions of each chiller that we provide the code in order to meet the specified heat load demand. Using this, we created a schedule of chiller operations with respect to different heat load demands taken from the plot prior. This schedule of chiller operation utilizes the optimal percent loads of each of the chiller to meet a heat load demand and to minimize energy consumption.
One additional area of inefficiency in the Collins Aerospace chilled water system is seen in the subpar performance of Chiller 4. Two possible replacements for Chiller 4 were provided by Carrier and analyzed by our team. Replacement option 2 was deemed to be the best choice, as it uses far less energy per load compared to that of the current Chiller 4 and replacement option 1. Using the schedule for chiller operation recommended by our team, an analysis of monetary cost and energy consumption was performed using both the current Chiller 4 and replacement option 2. This analysis concluded that replacing Chiller 4 would save Collins Aerospace around $67,000 per year.